shall we continue then? Okay, lecture 6. Now that we have our geometries, our energies, our orbital coefficients, let us proceed to calculating various properties. Depending on what your project is within the quantum tech CDT, you will be interested in different things. You may be interested in the straight energy electron density. You may be interested in spin properties such as hyperfine couplings, G factors, chemical shieldings, J couplings, and so on. Or you may be interested in some reaction intermediates that you hypothetically may or may not have in your system. So next couple of lectures we go systematically through the things that can be computed using standard software and annotate things as we go without really going too deeply into how exactly the software does it. Starting with the simple things, ionization energies, one could naively think that if an electron is sitting in an orbital, we could just take it away from that orbital, take it to infinity and nail it down there. At infinity the energy is zero. At some highest occupied molecular orbital it is whatever the molecule has. And so the Koopman's theorem from back in the day, the earliest Hartree-Fock type treatments, states that the first ionization energy is simply just minus the energy of the highest occupied molecular orbital. This of course neglects two things. Firstly, if you take the electron out, you create an imbalance of charge. The Coulomb properties of even the average Hamiltonian, even if the effective potential do change, and so orbital relaxation will happen. Orbitals will rearrange themselves to accommodate the charge, and so this theorem is an approximation because the orbitals of course do change when their occupation number changes. And the second thing, it's the standard ailment of single determinantal methods like Hartree-Fock. Of course, electron correlation is ignored, but that in principle can be generalized away if we use some post-Hartree-Fock or DFT method to account for at least some of that electron correlation. In DFT, as you know, orbitals have somewhat questionable physical meaning. They only have mathematical meaning as expansions of molecular density, but we could have a generalization of Koopman's theorem called Janak's theorem, which states, I will not prove it, I will simply only state here, that the derivative of the total molecular energy with respect to the occupation number of a particular orbital is in fact equal to the energy of the corresponding orbital. So this is how it is computed for DFT. And you do need a large basis set, of course, because we're dealing with energy, but thankfully it converges systematically. So if we look at the excitation, the ionization energies here, you can see that there is some basis set effect, but even in the CBS limit, we are pretty good compared to the double zeta basis set here in kilocalories per mole. If we take the opposite property, the electron affinity, so the energy of the molecule grabbing an electron and becoming a negatively charged ion, that is considerably harder to calculate. You can see you even don't get the sign correctly for the double and triple zeta basis set, and you do get the sign right in the quadruple, and if you extrapolate to the complete basis set limit, then hopefully that is correct. So the electron affinities are considerably harder because the perturbation in the totality of the electron structure is significantly greater if you add the electrons that shouldn't have been there and turn the molecule into a negatively charged anion. There are two types of ionization energies that we can calculate. Of course, the other thing that would change between the neutral molecule and the cation is the overall geometry. It can change a significant amount. So we can either do it like optical spectroscopists would want and consider a vertical ionization or a vertical excitation energy, and that is simply to do with the fact that these processes wherein an electron is taken away from the molecule usually happen quite quickly and the nuclei do not have time to rearrange themselves, and so in a lot of cases ionization would be a vertical process. However, if we do allow the molecule to rearrange, for example, the bond lengths, we would realize that the energy minimum of the ion is in a different place from the energy minimum of the original molecule with respect to the atomic coordinates, and we could calculate what's called an adiabatic ionization energy, which is the energy difference between the relaxed geometries here and here. So we can either optimize the geometry on either side of the ionization reaction arrow, or we can just use the same geometry for both, depending on the nature of the physics and chemistry that goes on in your process. You may want one or the other. An example of how this can be important: if we take a CH3 anion, so we pull a proton out of the methane molecule and leave the electron behind, it has this pyramidal geometry in the energy minimum, and of course the vertical ionization energy in this case would be huge, right? However, if we allow it to relax into the flat, right, the energy difference between the energy minimum of the pyramidal and the energy minimum of the flat in this excited state is actually much smaller. So this is an example of the huge energy difference that the geometry relaxation would cause here. And basis set convergence, you can see that's the ionization energy, that's the electron affinity. It really only converges at quadruple to quintuple zeta basis set level. So in all cases, it is a good idea to use as big a basis set as you can get away with. And if you have negatively charged anions, electronic structure significantly swells when the charge is negative on the molecule because, well, of the repulsion, and we would normally require diffuse function in the basis set. Diffuse functions overlap with a lot of things in the molecule. The number of 4-center and 3-center integrals would go through the roof, and so the calculation would become considerably more expensive as a result. Then the other related thing is electron density. We've already covered the basic definition a few lectures ago, but now let us look closer at it and at various parts that contribute to it, because we will now start slicing and dicing and partitioning and interpreting the electron density. So the overall definition of the electron density, right, is just the sum of the squares of the corresponding molecular orbitals, so Copenhagen interpretation of the wave function, and individual molecular orbitals are a linear combination of some atom-centered orbitals, for example, Gaussians, where the summation in here is over the number of the electrons, and in this case over the number of the basis function. So if we take this expansion and we substitute it twice into here, so the modulus squared is the function times the function conjugate transpose, and we take the sum, what we are going to have is this expanded version, right? We have a sum over mu here, another sum will be a sum over nu, and then we inherit the sum over the electrons over here. So let us take a look at this. If we integrate this over all space, what we are going to have is the total number of the electrons in the system. But what we are seeing here is two parts. We have this integral, which should look familiar. It's the overlap integral between the basis functions here. We saw it already when we built the Fock equation. And this strange thing we can rearrange a little bit more, so we keep the sum over the electrons and we retain the indices of the orbitals. And those of you who did spin dynamics would recognize an object that's vaguely reminiscent of the density operator. It's not the same, it is something different, electronic structure theory. They call it the density matrix, but not to be confused with the density matrix we have in spin physics. And of course this overlap matrix. And then if we look at what is happening here, we have a double sum over all orbitals. So what we do have, if we substitute that here and this there is what's called the Frobenius inner product of the two matrices. We have the density matrix contracted over both indices with the overlap matrix. But what is important here is we can now isolate contributions from individual orbital pairs, because this double sum is over orbital pairs. So let us take a closer look at what that means. Okay, so we have our n mu nu, so that's the contribution to the total number of electrons from a pair of orbitals mu and nu. We have the density matrix, roughly the orbital populations. We have the overlap matrix, so this same product here. And we have thus partitioned the density into pairs of orbitals. So why don't we use them to allocate which electron and which charge belongs to which atom? And this is quite approximate. We could say, okay, if the two orbitals are located on the same atom, then we can just assign all of the corresponding density to this atom. And we can interpret that electron density as contributing to the charge of that atom, approximately. If the two orbitals are located on different atoms, then in some sense the electron density is shared between them. And we can interpret it as contributing to the chemical bond. So we can start looking at the bond order. But of course it will also contribute to charges, because it is still the electron density. As you can see, it's approximate and philosophical, but in practice quite useful. And we can generalize such reasoning also to spin. We can calculate the spin density matrix, right, individually for alpha and the beta type orbitals in, for example, restricted or unrestricted Hartree-Fock procedure. This leads us to Mulliken populations and charges. If we take our nuclear charge and start subtracting the electron charges from it, so we start with the charge of the bare nucleus here, and then, as I've mentioned in the previous slide, we count all of the electron density where the two orbitals are sitting on the same atom as contributing to the charge of that atom. So electrons are negatively charged, so we subtract that quantity out of here. And then somewhat arbitrarily blame Mulliken, not me, that was 1960s, they had to do it approximately. If one function is on one atom and another is on the other, then we partition the charge equally between those atoms. Half the density to one, another half the density to the other. As you can imagine, this is hugely approximate because bonds can be polarized, but such is the definition of Mulliken atomic charge. If we ignore this Z and we put pluses in here, then we can simply count the number of electrons, and that's called the atomic population. If we count them including spin, this will be the atomic spin density. This is very roughly the amount of electrons with the charge, with the spin, that can be tentatively allocated to a particular atom. Now, this is of course only qualitatively correct, but well, no quantitative method exists anyway, because you cannot say, okay, we draw the line here and everything on the left is this atom and everything on the right is that one. That cannot be done. And so in the absence of a quantitative method, that might as well work. Very cheap to calculate, of course, it's a ground state property. You simply are looking at various straightforward mathematical operations with the orbital coefficients that you already know. And chemists like this, particularly pharmacologists, because this predicts charge patterns and electron density patterns in their molecules, and they can use it, for example, for docking. Right? Simple electrostatic binding of some ligand to some protein. This is generally good enough to at least, 5 times out of 10 predict what's going to bind and what isn't going to bind. But of course, such an approximate method would necessarily have problems. Diagonal elements of the density matrix may be larger than 2, in which case this philosophically implies a bond with more than 2 electrons in it, violating Pauli principle on how many electrons you can have in an orbital. They may even be negative, and of course then it doesn't make sense because we arrive at a negative number of electrons in an orbital. Equal partitioning, as I've already mentioned, is philosophically questionable. Diffuse functions, although they can span the entire molecule, they are still counted in atom-centered basis set as contributing to that atom, which isn't terribly correct either. And if you take those molecular atomic charges and calculate multiple moments of the molecule using those charges, they do not reproduce the exact calculated multiple moments based on the electron density to any reasonable accuracy. So something better is definitely required. And the better part, I will not explain here why exactly this works. It's a kind of orthogonalization. But Leodin suggested that we take this Frobenius inner product, right, so the trace of the density matrix and the overlap matrix, and you can do cyclic permutations under the trace. So you can break this overlap matrix into 2 square roots of it, rotate one around, and then of course this is exactly the same number as here, so we still have the same total number of electrons, but it's differently partitioned, and this quantity for various reasons is better behaved than the Mulliken populations. They're called Leodin populations, and when you use things like Gaussian, it will print that population statistics for you. Whichever one you ask for in the input, it will just give you the table. Not immediately useful, you know, in 2024, because we've moved far past such simplistic accounting of electron locations, charges, spins, and so on, but historically important and does give chemists a significant thing to interpret. They find it helpful. Okay, the same can be done to bond order if we look at all the pairs of orbitals where one orbital is on atom A and the other on atom B, and we sum up the corresponding part of the density matrix and the overlap matrix. We do get the bond order, so how many electrons, and of course 2 here is the fact that we need 2 electrons per bond, how many electrons contribute to a particular bond. And the results are actually pretty decent. If you look at propylene, if you look at something that should be a single bond, yeah, the order is 0.9. And then if you look at acetaldehyde, again, CO is supposed to be a double bond, so roughly there. For acetone, again, roughly there. So they do not sum up exactly to 1, 2, or 3, but they're actually not terribly far off, particularly for single and double bonds. Orbital visualization. You can plot orbitals in 3D space. Of course, they are not probability density, their squares are probability density, so they can be positive, negative, and even complex in situations where you have spinors, so spin-orbit coupled situations. But for Hartree-Fock, they are real, and you can just plot them, so green here for negative and red for positive, and that is one of the bonding orbitals of tryptophan in a little peptide that folds around the tryptophan called tryptophan cage. And again, this is useful for chemists, various reaction mechanisms, electron transfer, aromaticity, charge distributions, and so on, reactivity. They can interpret these things in terms of orbital overlap, and quite often you would see such visualizations in synthetic organic chemistry literature these days. Now, the interesting thing about Slater determinants, so if we put our orbitals into a fully antisymmetric determinant, those determinants are invariant under unitary transformations of molecular orbitals. In particular, what we can try and design is a transformation that localizes them. In a lot of cases, you would see pictures like this, where that is an aromatic ring, but you can see that the orbitals are delocalized across the ring and may therefore be somewhat difficult to interpret, and also rather inconvenient numerically because they can span the entire molecule if you have some conjugated system. What we can try and find is a unitary transformation that leaves the overall wave function, so the Slater determinant, invariant, but transforms the underlying basis in a way that localizes these individual orbitals. There are various ways of doing that. We could, for example, maximize the distances between orbital centroids, so that is one orbital, and so that's r. So that's the centroid position, so the average over the coordinate. That's the centroid position of some other orbital. Subtract the positions, that's the distance. Sum over all distances, maximize those distances with respect to this unitary transformation until everything is as far apart as possible. We could instead maximize the self-repulsion energy, so this pushes individual orbitals away from each other. This pulls a particular orbital inside itself as much as possible, so it collects it and localizes it as much as possible. Generally similar results here, but what you are going to see there is transformations like this. So that is, for example, the canonical molecular orbital that comes out of a Hartree-Fock procedure. If you do Boy's localization, you can see that the sigma bond here got localized, and then in some other orbital here there will be another sigma bond. So these are all delocalized, and every orbital here contains contributions from more than one unit of what chemists would consider a bond. But these localized versions, right, so that's the top part of the pi bond, that's the bottom part, that's the sigma bond, that's another sigma, that's another sigma. However, in some schemes, you get mixing between sigma bonds and pi bonds, so-called banana bonds, and this is mildly annoying. And so there's another criterion, Pipek-Mezy criterion, which maximizes the sum of density squares on all atoms. Yet another way of doing that, and that thing doesn't create banana bonds, so it retains the sigma bond in here and the pi bond separately, whereas the Boy's localization creates a banana here and the banana there, and you don't actually, so the sigma bond ends up split between these and this. So this is cosmetic, although this localization process does not alter the overall wave functions. Of course, such localized orbitals are no longer the eigenfunctions of the self-consistent field operator, so there's no such thing as the energy of a localized orbital, but it's a different kind of interpretation, roughly comparable to what we've just seen in terms of numbers from Malikian and Glaudin population analysis, just a more sort of three-dimensional density-based way of doing the same thing. So you will see a lot of this, and a lot of software packages would offer an option to localize the orbitals and then plot them, and these are a lot closer to what chemists consider natural than these highly delocalized situations here. What is important about localized orbitals is there's still a basis set in the same sense as the original ones had been, but because we pushed them away from each other, the overlap matrix becomes a lot sparser. The interactions between those orbitals are effectively weaker, right? So contributions to multi-center integrals get reduced, and so the efficiency of the calculation in this new basis set is significantly improved. So if we look at post-Hartree-Fock things like MP2, we can say, well, okay, why don't we restrict our excitations to be local? Because exciting an electron from one position to another position 10 angstroms away is probably unlikely. So we can make excitations local. We can ignore correlations between distant pairs of electrons because, well, they wouldn't see each other, they're too far. And so such approximations do make physical sense, and if we do perturbation theory in this localized basis set, we would actually recover most of the electron correlation energy at significantly reduced computational cost. So you can see here that is the CPU time in hours for full versus local, and the solid things here, circles and squares, are the full using the raw Hartree-Fock orbitals, and the empty ones are the localized versions of that. You can see significantly faster. And if you look at the corresponding energies, so for MP2, for coupled cluster, we do recover north of 97% of the corresponding energies at a much reduced computational cost. So these localization tricks are used a lot to cut the calculation time. Okay, so these were the densities and the populations and the localization, and that is to do with the electronic structure and with the way chemists interpret electronic structure. The second thing you will need, because this is the dominant mechanism of solid-state quantum device decoherence, you would have your spins or your unpaired electrons or your squid loops coupled to phonons, which are vibrations of the local crystal lattice. They will be distorting your Hamiltonians and destroying your entanglements. And in order to quantify such things, we need to calculate the vibrational frequencies and the normal modes, which are the directions in generalized coordinates for the displacement of the groups of atoms when a particular vibration takes place. What we can do is generalize a ball on a spring. We can say, okay, it's not just one coordinate now, it's a number of coordinates. So we start from some initial geometry and we perturb it somewhat, and that's the Taylor series. So the energy at the reference geometry, then the first derivative term in the Taylor series, so the gradient of the energy transposed times the displacement, plus the matrix of the second derivatives, the Hessian, and the two displacements, and divided by 2, because, well, Taylor series, you had that factorial of the number n in the denominator. And we've already looked at Hessians in a different context in the previous lecture. They are second derivatives of the energy with respect to the coordinates of every atom. So if our geometry is optimized into a minimum, then by definition the gradient is 0, so the Hessian is the leading term in the corrections, and under small displacements the series terminates here, and the Hessian controls the behavior of this energy under small displacements of atoms. And of course then this is standard vibrational analysis. If we diagonalize this matrix, we get normal modes, which are collective motions of atoms that happen with a particular frequency. That is the standard ball on a spring, Hooke's law energy, and the force is minus the gradient of the energy, so minus kx. So the spring feels the retaining force that's opposite to the displacement from the equilibrium. And then, as I've shown you in the previous lecture, you calculate the vibrational frequencies from the eigenvalues of this Hessian. So the square root of the force constant over the effective mass is your vibrational frequency. And these normal modes are important because they determine displacements. Displacements in some devices that you are going to build will determine the perturbations of the various magnetic interactions, and they would indirectly cause what's called spin-phonon relaxation. But we'll get to that in a few lectures' time. So this is how vibrational frequencies are calculated if you know the Hessian. And now let's look deeper into what is involved in this process and what the pitfalls are. The trouble, of course, the principal trouble, is we've just made a quadratic approximation. We truncated the Taylor series, and really in practical molecules that is rarely an awesome approximation. It's a pretty good approximation for a couple of first energy levels. That's your Morse potential that typically describes bond dissociation, and that's the harmonic approximation. And you can see a couple of energy levels in here are close, but then they get further and further away. And we are stuck with the Born-Oppenheimer approximation. To us in computational chemistry, nuclei are point charges. So, and we've pinned them down, right? We assume that the nuclei move much slower than the electrons, and so we consider each geometry fixed, and then electronic structure theory problem on top of it. And so all of these approximations combined mean that when we calculate vibrational frequencies in this way, they come somewhat shifted by a constant scaling factor. And that scaling factor is broadly 0.96, 0.97, and it depends on the basis set, the method, the molecule, and so on. So these are scale factors, and you can see the familiar Popple type basis set with all the polarization and diffuse functions in there that you have already had the time to explore. That's the root mean square error in wave numbers, I think, on the vibrational frequency, and that's the scaling factor that is required to put the centroids of all the error distributions in the same place. We could, in principle, of course, also calculate third derivative, fourth derivative, or even scan this bond distance explicitly, in which case we will get something that looks like a Morse curve. You've seen that in a few previous lectures, but that is very expensive, particularly for molecules that do have large number of vibrational modes. But you can ask software, Gaussian in particular, to do numerical differentiation in the direction of every normal mode and estimate the unharmonicities, which are higher derivatives with respect to displacement, and those are in fact visible in vibrational spectroscopy if you look very carefully. Which brings us to spectroscopy and to contributions of all of these motions and effects to thermodynamic properties of the molecule. Those of you who did statistical thermodynamics, I don't know if chemists even do it these days, will remember something called a partition function, which is the sum of the exponentials of the energy divided by kT with these degeneracy factors over all of the energy levels. And if you have multiple identical molecules in the system, so n identical molecules, then you have to take a single molecule partition function to power n and divide it by n factorial, because molecules are indistinguishable, and so there are n factorial permutations of indistinguishable objects out there. And then you have the internal energy, which is just your electronic energy, and then the temperature contribution, which depends on the derivative of the log of this. You've got the entropy, which is the straight Boltzmann thing, which is k log q, the thing that is carved into Boltzmann's tombstone, and then the temperature factor, again, depending on the derivative of this q. The enthalpy is the internal energy plus PV. The Gibbs free energy is the enthalpy minus Ts. And all of this begins its calculation process with just a single molecule and the partition function of a single molecule. You would have electronic degrees of freedom, so the summation over all the electronic excitation energies, times the translational degrees of freedom, times the rotational degrees of freedom, times the vibrational ones. Well, translational and rotational are easy, because we just say, well, okay, let it move and let it turn as a rigid solid body, at least to some approximation. This electronic we also easily know, because we know all of the excitation energies, and this vibrational one comes out of the Hessian. So the total internal energy is electronic is our reference point. We just assume we are sitting in the ground state, and the reference point is arbitrary if we are looking for energy differences. Then translational one is 3/2 RT for the ideal gas. The rotational one, likewise, unless you have a linear molecule, in which case this number is modified. And then vibrational one is just the usual sum over all of the vibrational frequencies. And of course, for a molecule that moves and rotates as a solid body, that doesn't depend on the molecule, that doesn't depend on the molecule, but this does, because this contains vibrational frequencies. Then we put this together. And of course, PV equals nRT, and then if n is the same, then PV equals RT, right? Or at least is proportional to it for an arbitrary amount, but for 1 mole it is equal, so this is U plus RT. And then the entropy is the complicated beast. You do have electronic degrees of freedom, that's the ground state spin, so that would have a number of states in there. Translational entropy, rotational entropy, that depends on the inertia tensor, and then the vibrational entropy from the vibrational statistics. All of that is put together, thankfully automatically, by the more sophisticated electronic structure theory packages. Whenever you request vibrational analysis, for example, from Gaussian, all of this is calculated for you automatically and printed to the log. Thank goodness, because in a lot of cases we do need all of that if we want chemical accuracy, because entropy does really matter for a lot of molecular rearrangements. If we do have a chemical reaction, then the change in the Gibbs free energy is of course the sum over reactants minus the products. I think it's actually the other way around, so stick the minus sign in front. And if we are dealing with complicated thermodynamic processes, for example ionization, this is important for calculating the acidity constants, important in pharmacology, then you have to deal with a lot of complications. If we are looking at some acid in its protonated form, of course, dissociating it in the gas phase is a really bad idea, because Coulomb interactions would be wildly overestimated by a factor of 80 in the case of aqueous solutions. So what we need to do first is to calculate the energy of solvation, to put it into water, energy of solvation here, energy of solvation there. So these individual arrows are easy, right? One calculation in gas, one calculation in some polarizable continuum. We'll talk about it a few lectures from now. And so the energy differences here are easily calculated. The energy difference here is easily calculated here. And so this complicated cycle, because it has to sum up to 0, then allows us to find out the Gibbs free energy of dissociation in the aqueous phase. And even that is a problem, because of course H plus is a bare proton. It doesn't have electrons, and predictably electronic structure theory packages somewhat dislike particles that don't have any electrons on them, so you would have certain difficulty persuading Gaussian to consider an electronless proton. But of course in real solution it's not just a proton, it's actually H3O plus, the hydroxonium ion, which is formed, so a water comes in, grabs a proton, and so you have the anion here, in which case it's a somewhat more complicated thermodynamic cycle, but this generally allows people to get energies sufficiently precisely, assuming that the method is good and the basis is large enough to get the pKa's, the acidity constants, to plus or minus 1 unit, which is, you know, not too awful. Okay, that's it for properties for today. So we looked at the things that are either ground state or not too far from the ground state. In the next lecture we will take a look at the properties that do involve electronic structure excitations and all of the associated effects. Any questions?